I'm Greg Wheatley, and my guest today on Inside Wheaton is Dr. Thomas VanDrunen. Tom is Associate Professor of Computer Science here at Wheaton College. Tom, it's great to welcome you to Inside Wheaton.
Thank you for having me.
Tell me about how long you've been at Wheaton College.
Just finished my 10th year.
And came here, is this your first academic post?
Yes, it is. I came here straight out of graduate school.
Okay.
Right.
Well, tell me about coming to Wheaton. It's always interesting to hear people's stories, how they connected with the college and how they wound up teaching here.
For quite some time, I had been very interested in Christian higher education, and when I went to graduate school, that was what I wanted to do. I wanted to teach at a Christian college, and I didn't go to Wheaton as an undergraduate. I went to Calvin College in Grand Rapids. But
that's an okay school.
But I grew up in the area and always had a lot of respect for what Wheaton College was all about and the role that it has played in the evangelical community. And when I was in my last year of graduate school and starting the job search, I actually looked at a very wide range of schools as not knowing what the availability would be of different positions, and I applied to all different shapes and sizes of schools. I think in total it was applied to 40 different positions. But very quickly the position that in God's providence was open at Wheaton became the top choice. I remember coming to interview on a snowy day, and that is what the Lord had in store for us.
Well, it's a wonderful story. Tell me, as you mentioned computer science, it strikes me that a lot of us aren't sure exactly what that means as a discipline and how it fits. Is that in the mathematics department here at Wheaton?
It is in the same department as math. It's the math computer science department. And I think one thing that can bring about some of the confusion is that the name computer science can be applied to a fairly diverse set of things at different schools. Some schools you might see the label computer science given to something that might be more kind of a vocational IT program, and that's really not what we do. And also, the character of the program is affected a little bit by the fact that we are in a math department, not an engineering department. But computer science, as the science of computing, deals with problem solving, deals with classical problems of how to organize information, how to compute things from that information. A good deal of the instruction in computer science and a computer science curriculum is going to be computer programming, but we like to emphasize that computer science is not equal to computer programming. Computer programming is a skill that you need to have in order to do the sort of problem solving.
Let me see how I'm doing on this.
Sure.
Sounds like it's more theoretical than some of those. So when you say it's not vocational, is it more of the theory of?
Well, I would say there is a strong theoretical component to it, but that's certainly not all there is to it. In what we do, there also is a strong component of building things, and when we have courses in things like operating systems and networking, not only are we looking at classical problems in networking, but it's also important that to learn these things, students have experience building systems. We have a software development course that all of our sophomores take. They jokingly refer to it as sophomore development because it's such a formative experience for them. But something like that is very experiential. And most of the work in that project, most of the work in that class goes into a semester-long group project. So there are plenty of ways in which it is a very craft-oriented a discipline, but the mathematical, theoretical aspect of it is there all along as well. Another thing that would differentiate what we do from, say, a program that's more a straight software development vocational program is that in our curriculum, we try not to have things geared towards things that are trendy. I mean, we certainly keep current, but our philosophy is that we need to be training students for lifelong learning, teach them to master the fundamentals that will allow them to self-train for all of the changing trends in computing-related vocations.
Certainly such a fast-growing field, right? I mean, I remember taking a computer class in high school, and this will obviously not only date me, but it'll probably make you laugh as a younger person. I remember it was the language was basic. We were typing on a dumb terminal basically and spitting out punch tape.
Right.
And you've probably read about that in history books, right?
Well, my first experience was with BASIC as well. We had an Apple II Plus growing up, and that's where I got my first taste of programming. So,
but it's a huge, it's a fast curve, isn't it?
Oh, sure.
And to think about where we are today. Tell me what, in your view, Tom, all of that has done to us as people and as a culture, a society. I don't think any of us can envision now doing anything without computers.
Sure.
And yet it hasn't been all that long that wasn't true. So what does that do to us?
Well, I guess there are a few ways to think about that. One we can think of is how does the availability of the sort of technology that's enabled by computing and the availability of information that we have on the internet, how does that affect the way we think of ourselves, the way that our thought processes and things like that, and some of those things have been studied and written about. I don't think I've looked at that in deeply as some of my colleagues have, but I guess there's another way that you could look at that and say, how does the advent of the craft of computing affect us? I mean, that's how I like to excite my students in an introductory programming course, is to show them how programming is an outlet for creativity, and that software is such a flexible medium that I think that, and your question is, what does that do to us? I think it gives us a great opportunity to express the creative faculties that God has given to us.
That's very interesting, because I think a lot of times we think of anything math-oriented as sort of binary, black and white, cut and dried, but to hear it put forth as a creative endeavor, and of course then that's going to bring in the whole Christian component and worldview.
Sure. And I guess I would say, as a side note, just to, for the sake of my math colleagues, I would want to emphasize that there is a very important creative side to mathematics at the college level as well.
Right.
All the working of writing proofs requires a lot of creativity and thinking through that. But as you were saying, I think that there is quite a misperception about what computer science in general, and then programming and software development in particular, is about, and it's too easily dismissed as something simply for geeks. But I try to invite students in our introductory programming courses to see that programming really is for everyone. It's something that, I mean, not everyone is going to be a complete expert. Not everyone is going to be a coding genius, but it is something that is still accessible to the general population. People can, almost anyone can learn the basics of programming and find it useful, and not only for solving computational problems, but for making things that can help people, be of use to people. I mean, we see that in the availability of apps that people use every day. That's the sort of thing that many people can learn how to code and produce.
So if I were to walk up to your office tomorrow and say, I know nothing, teach me a little bit about writing code. Is that what you call it? Writing code?
Sure, yeah.
Source code, whatever. Where would you start with me? I mean, what would be sort of a practical entry-level way that you would talk to me about that?
Well, I think what I would do is introduce a kind of minimal programming language. I'd take something from a common programming language like C or Java or Python, and I would just tell you about some of the most basic features of it. Say these are some of the things you would need to know in order to manipulate some data. And then I'd say, let's take some simple problems. And for simple problems, they'd have to be largely based on numbers. Mm-hmm. I mean, I don't think that on day one I would know how to walk you through something that would have a lot of glitter to it.
Right.
But I would say let's take the problem of, we have a sequence of numbers, and what we want to do is sort them. We want to put them in order. And I would have you think about, all right, well, let's suppose that you were doing this just on on paper or a tabletop thing. What if you had a bunch of cards with these numbers? You know how to put them together. What you need to do is stop and think about the patterns of thought you're using, the algorithms, to use the real word. What algorithm are you using to put these numbers in order? All right, now let's see if we can take that process and write instructions for it. And a lot of the first lessons in programming are all about taking things that we already know how to do, whether it's putting numbers in order or doing long division or anything like that, solving a maze or some other kind of puzzle. And now, how can we take what we're able to do off the top of our heads and make a set of unambiguous instructions, which you can then express in a programming language, feed to a machine, and have a machine do it. Now, one example I like to give, this actually comes up in one of the classes that I teach. Let's take something like a Sudoku puzzle, and this might explain a little bit about the way I think. I don't think I have ever sat down and just solve a Sudoku puzzle on paper. It actually doesn't sound that interesting to me. When I first learned about Sudoku puzzles, I thought what would be really interesting is to find a way to automate the solving of this. How can we write an algorithm so that a computer can solve a Sudoku puzzle? Now that sounds like an interesting task to me.
That's why you teach what you teach, right? Yeah.
Now that's not. I think that would be a pretty high task for someone just walking into the first day of programming to do. But once someone gets a little bit of sophistication in knowing how to put together algorithms, it actually, I think, is a fun problem to walk through. How can we take this, these steps that people can do in their heads? What are the steps that they're taking, and how can we communicate that to a machine and automate it?
What do you think? I can't have you in here without approaching this question with you a little bit. What do you think about the whole idea, and the term for it escapes me now, but there's a specialized term where it's basically the idea of a cyborg, where human cognition merges with,
right.
There's some fancy
Well, I think
term,
you're thinking of artificial intelligence.
Artificial intelligence, and there's some word where someone has projected by such and such a year that will happen.
Well, I mean, I can comment a little bit on the idea of artificial intelligence. I'm not an expert in this, but just as someone generally in the field of computer science can observe a little bit of what's going on. One can talk about the general promises of artificial intelligence, that the idea of making something on a machine that will mimic what humans do. And some of the claims of what would be brought about by that, I think are greatly overblown. On the other hand, there are some very specific projects that sometimes fall under the general term of artificial intelligence that are very interesting, very useful lines of research. I mean, I would say as a side note that I'm not a big fan of the term artificial intelligence as a subfield of computer science, simply because it seems like any research project that makes a lot of progress in artificial intelligence then becomes its own thing, and then goes by that name. Now there are things like automated theorem proving. That's something that is useful in mathematics. That is to make it a method in software for constructing a proof for a mathematical theorem. That's a very I think a very interesting line of research in the boundary of math and computer science. There's the field of machine learning, and that essentially uses statistical approaches to teach a machine to do something. And an idea would be, if you're having a machine that would drive a car, a self-driving car, in a machine learning system, you can feed in a large amount of data about, what if the cameras see this situation on the road and the other cars in the road are in this position. Then in this case, the car would need to slow down this many miles an hour, or then we need to turn or swerve, something like that. Have a large amount of data, and then have an algorithm that from that can produce a general rule, which then controls the car. I mean, those are the sort of things that go on in machine learning, and that also, I think, is a line of research that has produced, and I would anticipate will continue to produce a lot of very useful things. But that certainly is something different from this idea of making something that you have to raise questions of consciousness about.
Exactly.
And so I think that the lines of research that are producing real, very useful technologies really kind of fall into a different class than things that raise more philosophical issues. And I think they also have a lot more promise of making progress.
Yeah. Tell me about the textbook that you're finished with, still writing?
It's been out for almost 2 years now. It was, August 2012 is when it came out. So I've been able to teach with it for 2 runs of that class. The class that it's for is a fall class, so I've taught it with the fall this past 2 years. The textbook is titled Discrete Math and Functional Programming, and I usually find that for people who are not in math or computer science,
reading.
that title is a showstopper for a conversation stopper for almost anyone. But and I also have plenty of people who make fun of the word discrete, and this is discrete as DISCRETE, not EET.
There you go.
So here, discrete is the idea that we're dealing with quantized, individual, atomic mathematical objects. I guess a quick way to place what discrete math is for people who aren't familiar with that is most of the math education in late high school and early college is all about getting people ready for calculus and then teaching them calculus and teaching them things to do with calculus, which is great. I really enjoyed calculus when I was in high school and college. But in all of that, there are a whole bunch of other mathematical topics that simply get pushed to the side, and calculus is one of the most important ideas that students need to have in getting to calculus is the idea of a continuum. You have the real number line, and any place in the real number line you can have a segment and you have just as many things inside that segment as the entire line. In discrete math, we're dealing with areas in mathematics where you don't have a continuum, you have discrete objects. So those are things like sets, we do Boolean logic, and functions and relations, and other things like that. The reason why that's of interest to me in computer science is that a lot of computer science concepts, both in kind of programming, the more applied side, and also the theoretical aspects of computer science, rely on a lot of these discrete math concepts. And so it's very important that there be a discrete math course in a computer science curriculum. And there's nothing special about what we do. I mean, there's essentially any computer science major program is going to have a discrete math supporting requirement. What is interesting in what we've done is the other part of the title, the functional programming. Functional programming in this case refers to a specific style of programming, or paradigm is the word we use, but paradigm is kind of overused generally. And in functional programming, we view a computer program as a collection of interacting functions in the mathematical sense, hence the name. That's as opposed to viewing it as a sequence of instructions, which would be what we call imperative programming. Now, what I've done that's somewhat novel is to combine these two ideas of discrete mathematics and functional programming into a single course, our Computer Science 243, and then wrote the textbook that goes with that, so that on one hand, the mathematical topics are a little bit more palatable to the computer science majors because that course endeavors to show immediately how they inform what we do in programming. But I've also envisioned that course as a way to introduce math majors to programming in a way that's familiar to them. The slogan I like to use for that course is that computer science majors should learn to write proofs, and math majors should learn to write programs together. To do those two tasks as a single endeavor. So that has been a very enjoyable project. I'm still working on supplemental material for that.
Well, Tom, great to get to know you. Thank you. I want to invite people to get to know the math department and the computer science department here. Maybe you or one of your students is interested, and if so, just get in touch with wheaton.edu, and you can learn a lot more about the department here, and it might just be a good fit. Dr. Tom VanDrunen is Associate Professor of Computer Science. Tom, thank you so much.
Thank you. Good to be here.
For Inside Wheaton, I'm Greg Wheatley.